such that paper publishers die and publication becomes totally electronic. That's the way things have to go. Anyway, all right. Now, third question, well, it's question 3 in the text. It's the second question on this board. It's effectively a Heisenberg uncertainty principle. It's pretty simple, just a few lines. But to give you an idea, you're given a particle. You're told that its mass is m, and that particle is confined in a box, and the box is incredibly small. Like it's Planck's constant. The size of the box is Planck's constant divided by mc. Right? Now it's in the box somewhere, but you don't know where exactly. Right? So that means that you have an uncertainty in the position, the delta x, that will be of this size. It's confined to the box. Right? It's somewhere in that box, and the size of the box is h over mc. Right? So that is your delta x, the uncertainty in the position, right? H over mc. And you're asked to show that the uncertainty in the momentum, so delta p, is such that the particle is moving pretty well relativistically. And what that means is that the speed of that particle is pretty well close to the speed of light, right? Its velocity is so close to the speed of light that its mass will go up, and all that kind of stuff. All this weird special relativity stuff. Okay, to say that something is moving relativistically means that its speed is very close to c, the speed of light. All right. Okay. Now here's the uncertainty principle. Delta x delta p. So the product of the uncertainty in position times the uncertainty in position and the uncertainty of the momentum is of the order of Planck's constant. Right? Actually, it should be greater equal, but we'll do the uncertainty principle in greater detail and a more accurate, and we'll derive a more accurate form for the uncertainty principle later. All right. Well, delta x, we just plug this in, right? So h over mc. Now the momentum will just be the uncertainty in mv, right? That's what the momentum is. By definition, it's just the mass by the velocity. So for p here, just put mv. So let's assume the velocity is not so great that the mass shoots up hugely. So let's say it's roughly equal to the rest mass. So let's cancel. We can cancel these two m's. We've got h on both sides, so we can cancel the h, Planck's constant. And what are we left with? So we're just left with 1 over c delta v is roughly 1. Okay, so take the c over, so you got the uncertainty in the velocity is about c, speed of light. So that means you're not sure what its velocity is. So the uncertainty velocity is about the speed of light. So in other words, that particle could be moving very fast, right? Because the uncertainty velocity is of the order of c. So in other words, the velocity is more or less relativistic. Okay, so that's pretty easy. Right, now the third question on the board, which is question 5 in the text. There are 7. All the questions at the back of the book, right, in Appendix F. Okay, so I've done 3 of 7. I usually do third or half in the problem-solving session. Okay, so you're given a wave function, so of this form. Now the r here is just the radius. So let's assume you have a spherically symmetric wave function. So the further you've got a center here, and everything's spherically, like as in a sphere, spherically symmetric. So as you move further and further away from the center of this sphere, the wave function here, now remember, look on this as an amplitude. Remember, you square the amplitude to get the probability density. That's Born's idea. So this probability density is dropping off with the radius, the distance to the center. Okay, so as r gets large, this amplitude here is going to go to 0. It will asymptote. You know that word? It means get infinitely close to a given line, usually a straight line. So this will asymptote to 0 as r gets large. Right? So it's r underneath. So you're given this wave function, this waveform, and you're asked to find the probability flux or current. Same thing, flux current. Right? Now I've written up here the definition. We did that. It was pretty well the last thing we did in theory session. Now if you're going to see psi as an amplitude for a probability density, you can actually find a formula using Schrodinger's equation for the flux density or the current density, same thing. Okay, and here's the formula for it. And you asked to calculate this flux. In other words, using this particular wave function, this particular psi here, taking this form. And you're asked to calculate the flux, the probability density. How much is the probability increasing in a given region over time? It's not just the probability; it's the probability density, but the flow, hence flux, or the current, same thing. And you're asked to show that it's equal to this. All right. Now, I haven't done every line. Again, after a while it just becomes algebra, a bit tedious. Okay, so here's the formula for the flux or the current. That's from the theory, end of the theory session, previous session. Okay, so I've just put it up again here to remind you. So, now, instead of using x now, we're assuming this is spherically symmetric, right? So it doesn't matter what r, which direction your r, or the radius is. Think of it just as a scalar, not as a vector, right? So instead of having d psi by dx, you just have dr, effectively the same. So I've rewritten the flux here. Instead of dx here, I've got dr, right? Well, then it just becomes mechanical, it just becomes algebra, so a little bit of calculus with complex number theory. So calculate d psi, dr, right? So you just differentiate this with respect to r, right? And well, here's your answer. So you differentiate this part first, and then differentiate this. The differential of uv is u dv minus v du, remember from calculus? So you get two terms for this, and similarly for the conjugate, a bit of revision. Remember what the star means? If you see this star here in this context, in the context of quantum mechanics, if you star this psi function, it just means everything in your formula for psi, you convert the I, the square root of minus 1, the I to minus I. So if you conjugate or you star this psi, everything here stays the same except this I here becomes minus I. Okay, that's all it means. Pretty trivial idea, right? So if you differentiate now, psi conjugated, you'll get these two terms, which are similar to here, but now you've got minus I instead of plus I. Yeah? Minus I. Oh, and I didn't bother writing out all this stuff. I just put it like here, blanks. But for these blanks here, you just you can fill that in there if you want. I didn't bother with it. Okay. All right. So now you can find. So now that you know these two, you can find the product of psi star d psi dr, and I've skipped a few line or two, but anyway, you get these two terms, right? Do this as homework. convince yourselves that this is true. Now, a similar story for psi d psi star dr. Again, you get these two terms. Now you need to take the difference between these two terms. So if you take the difference between these two terms, these, since they're the same, they all cancel out, right? And you got that. Is that right? Yeah, that minus that. So minus minus gives you plus. So you just get double this, right? So you get 2a squared ik over r squared. Now the flux is defined, or the current is defined as minus I h bar, that's Planck's constant divided by 2 pi, remember this h bar, divided by 2m. So here's this term here, and this just put in here, and so this, which is equal to this, you plug this value into here. Now lots of stuff will cancel. You get minus I squared, that's just 1. The 2's will cancel, and you're just left with a squared over r squared k h bar divided by m, and there it is. Okay, so that's the end of the theory session and for lecture 1. Now lecture 2 we will start by taking the Schrödinger equation, and we will in a sense split it up into a part that depends on time and a part that does not depend on time, depends only on the position. And then the part that depends on time, a bit more complicated. So for a chapter or so we will deal with the Schrödinger equation, which is independent, the time independent form of the Schrödinger equation, and we'll solve problems with that. Now the physics community before Schrödinger invented his famous equation was very familiar with DE's, differential equations. So next chapter, if you're familiar with solving DE's, differential equations, you'll probably find this next chapter fairly familiar, because because that's essentially what it is. It's just solving differential equations for certain circumstances, and certain continuity conditions have to be met. If you don't know what I'm talking about, don't worry. We'll do it next session. Okay, so I'll stop there and see you for lecture 2, which is called, just a minute. Oh, it's just simply called Wave Mechanics Part 1, right? And the first section of lecture 2 is called Time Independent Schrödinger Equation. Okay.